Okay, so welcome back to the second lecture of this morning. Nick is going to talk today about cycle integrals of the J function by Duke, Imamoglu, and Toth.
Thank you. All right, this is the last one of these lectures. We've actually heard a lot about these cycle integrals already by Balesh and Vaibhav and others. So some of this will be repeat. I hope that's okay, because maybe my aim is slightly different than theirs. They were trying to talk about exciting, new, interesting research, and that's not my intention today. I want to show you the details of how this all works. So I'm going to try to get into the nitty-gritty and actually do the computations, and hopefully that'll be good. So there will be some overlap. So yeah, just be aware of that. So let's start. I have lots of definitions right at the beginning before we do anything interesting, so let's just get through them. So let's start by having a number little d, that's 0 or 1 mod 4. And we'll call these discriminants. No other assumptions about little d yet. And then we'll define script q sub d to be the set of q's of the form ABC. So these are quadratic forms of discriminant d. So b squared minus 4ac is equal to d. And then I also want to assume, and this is an assumption that's sort of self-contained, so I'll put parentheses around it, a is greater than 0 if d is less than 0. So in the case that the binary quadratic form is positive, or is definite, I want it to be positive definite, and I want A to be positive. Okay, so the group gamma, which is PSL2Z, acts on quadratic forms. And we've seen a description of how that works in other talks. For us today, the exact description is not going to matter. So I'll just say there is an action. And if this results in finitely many classes. QD mod gamma. Okay, and actually this is a group. It's a finite abelian group, which is not at all obvious from the definition, but it turns out that it is. So we're going to let gamma sub q be the stabilizer of q. So it's the gammas in gamma, such that gamma q is equal to q. And let me tell you about this group, or this subgroup, in the various cases. So if d is negative, then the size of gamma q is either 2 or 3 or 1. It's almost always 1. And there are two cases in which it's 2 or 3. So it's 2 if q is related to A0A. And it's 3 if q is related to AAA. And otherwise it's 1. So it's safe to just think of it being 1 all the time, because you'll get it right most of the time. Okay, so if d is positive and d is not a square, then gamma of q is actually it's an infinite cyclic group generated by this distinguished element, which I'll call g sub q, where we can actually write down exactly what g sub q is. It's plus or minus the group element t plus bu over 2, cu minus au t minus bu over 2. And t and u solve a Pell equation. T squared minus du squared is equal to 4. Okay? It's not too surprising that this Pell equation shows up, because these, in the positive d case, you get quadratic forms which relate to real quadratic fields. And in real quadratic fields, there's a fundamental unit which generates the unit group, and the fundamental unit, the coefficients of it are exactly given by the Pell equation. So this is not too surprising. Okay, and if D is positive and a square, well, I don't want to talk about gamma Q anymore. I'll actually just tell you exactly what the whole group looks like. Because in this case, I can actually describe the whole thing very easily. So I'll just tell you exactly what Q d mod gamma is. It's A, B, 0, such that 0 is less than or equal to A is less than B. And what is B? Well, instead of writing square here, maybe I'll just say D is B squared. Okay, so that will tell you, that just tells you about the whole group. Okay, any questions so far? Some more definitions. Let's talk about some geometry. I didn't draw my lines. It's going to mess me up. Okay, so some geometry. So if D is negative, there's a distinguished element of the upper half plane called tau q. It's minus b plus I square root of absolute value of D over 2a. And this is root of q tau 1 in the upper half plane. Remember, I'm assuming A is positive, so this actually is in the upper half plane. And it turns out that the action of gamma plays very nicely. So there's two actions here. There's an action of gamma on quadratic forms, and there's an action of gamma on elements of the upper half plane. And it plays very nicely with this tau. It just moves like that. So if I change the quadratic form to an equivalent element, that just changes the element of the upper half plane to an equivalent element. And so because of this, if you like, we can assume that tau q is actually in a fundamental domain for SL2Z that we've seen before. So this is the unit circle, and then here this is minus 1/2 and 1/2. So this gives us a point in the fundamental domain. Okay, these quadratic forms. So if D is a fundamental discriminant, the quadratic form representative that goes with the tau q in the fundamental domain, these are called reduced forms. And Gauss has a whole theory of reduced forms, and that essentially corresponds to this tau q just being in the fundamental domain. Okay, so if D is positive, we'd like to do something similar, but there's nothing in the upper half plane that really naturally goes with tau q, or at least not a point in the upper half plane. So what we'll do is we'll still look at the roots. Oh, and I want to assume that D is not a square for now. So the roots of q tau 1 are real numbers. They're real quadratic numbers. So they sit on the real line. They don't sit in the upper half plane. And so what we're going to do, let's call them something. Let's say they're W and W prime. So let's let SQ be the geodesic in the upper half plane connecting W and W prime. So this will look, if we draw a picture, so like let's say here's W and here's W prime, this will be a semicircle centered on the real line. So this thing is SQ. In this hyperbolic geometry, this is a straight line connecting W and W prime. And we should put an orientation on this, so we'll orient this. Oriented, let's see, so it'll be counterclockwise. if A is positive, and clockwise if A is negative. In the case when D is positive, we can't just assume that A is positive or negative because we could have both. So we'll have some orientation on SQ. Okay, you can write down a formula for SQ exactly, and it's not too complicated. It just looks like A absolute value of tau squared plus B real part of tau plus C is equal to 0. This is not a hard calculation. If you just write tau as U plus IV and just work this out, this will give you the equation of a circle that's centered exactly halfway between W and W prime, and you can just see that exactly. So what we want is actually something finite, so the length of SQ is actually infinite. We want something finite, so what we're going to do is let CQ be SQ mod gamma Q. So we're going to mod out by the stabilizer of Q, which remember is infinite cyclic, and then we're going to pick, essentially one way to realize this is to pick any Z in SQ, and then CQ will be the arc connecting Z and GQZ, whichever arc connects those in that orientation. So remember, this GQ is a generator of gamma Q. Okay, so what does this look like on the picture? We just pick any Z here that we want, and then we find GQ of Z, and this little piece here will be CQ, and that's going to now be a finite length piece of SQ. This is very nice. So the length of CQ is actually maybe some constant times the regulator of Q adjoint square root of D. Again, if D is fundamental, then that will be true. So there's already some interesting algebraic number theory happening here, even just in this setup that we're doing. So I guess I have one case left, which is that if D is positive and a square, well, I want to do the same thing, which is to draw a geodesic, but now I don't have an SQ or I don't have a gamma Q to mod out by, and so I'm going to end up with an infinite geodesic no matter what. Log of the fundamental unit. Yeah, and it might be 2 times that or 4 times that. So like there's some constant, but yeah, it's going to be given by log of the fundamental unit. Okay, so let's do this carefully. So the roots of, and now I want to take the roots of QXY equals 0. So these are in P1 of Q. So I'm thinking of like projective rationals. So meaning that, okay, what I really want to do is think of this as x over y. If I find a root of this, I want to just take x over y, which will be a rational number. But it could be that y is 0. So I need to also allow for a point at infinity. So if you like, you can think of this as just the rationals union infinity. And hey, well, those are all the cusps of SL2Z. And so these geodesics, they connect 2 cusps. So we're going to let CQ in this case, well, it's just going to be SQ as usual if A is not equal to 0. And we're not going to mod out by gamma Q because there's no gamma Q to mod out by. So this will just be an infinite geodesic. And if A is 0, it will be, so CQ will be the vertical line with equation real tau equals minus C over B if A equals 0. So this will be a geodesic connecting some rational number to I infinity. And that's going to have infinite length. Oh, and let's say this is oriented upward. Okay, that's a good place to pause for questions. How are we doing on the setup? Is this okay so far? All right. Let's do some more setup. So let's let big D be a fundamental discriminant. This word has been used a lot, and I don't think anybody's defined it, so why don't I actually define it finally once and for all. So this means that D is either 1 mod 4. I guess this isn't really a definition so much as just maybe a property. D is congruent to 1 mod 4 and square free, or D is 0 mod 4, so D is equal to 4, say D prime, where D prime is congruent to 2 or 3 mod 4 and square free. So maybe a definition would be that D is the discriminant of a quadratic field. So it's going to have this form. Okay, so then there's this character, which has shown up before, chi D of Q. And I believe we've seen a definition of this, but I'll say it again. So it's D on N, the Legendre symbol, if Q represents N, and the GCD of A, B, C, and D is equal to 1, and it's 0 otherwise. So this chi D goes from Q, let's see, quadratic forms of discriminant little d times big D, mod gamma. So notice that big D here is not necessarily the discriminant of the quadratic form, but rather a divisor of the discriminant. So it goes from this group to 1 minus 1 or 0. So this is a generalized character. And if we restrict to just the primitive classes, meaning those for which the GCD of A, B, and C is 1, then you'll never get 0, and so this is a true character of that like restricted in that case. And this generalized genus character has the property that chi D of minus Q is the same thing as sine of D times chi D of Q. When we're talking about negative discriminants, we don't really care about negative Q, but when we're talking about positive discriminants, we will care about that. Okay, a little bit more setup. We're almost ready to start some interesting things. So we've seen these functions a lot. J1 is J minus 744. And then Jm, more generally, is going to be whatever modular function starts Q to the minus M plus big O of Q. This is going to be some polynomial in J1. Okay. And now I can finally define the objects that we're interested in. So these are going to be called twisted traces of singular moduli, or twisted traces of cycle integrals. And so this is going to be one thing if little d times big D is negative, and it's going to be another thing if little t times big D is positive and not a square. Okay, so if it's negative, I have a little normalizing constant here, 1 over square root of D, and then we're going to sum over all the quadratic forms of discriminant little d times big D mod gamma. We're going to twist by this genus character, chi D of Q. And then we're going, let's see, I actually wanted to do that as the numerator of a fraction, so chi D of Q over the size of gamma Q, which remember is either 1, 2, or 3. And then we're going to plug tau Q into Jm. Okay, so the theory of complex multiplication tells us that the numbers that we get out of these Jm's, these are algebraic integers. And when we sum over all of the classes, this is a trace of an algebraic integer. It's going to be an actual integer. Okay? So We've seen these before. We've also seen these second things before. These are going to be the cycle integrals. So that's again a sum over classes twisted by chi. And now instead of plugging in tau q, which we can't do in the positive case, we will take an integral over CQ. And remember, this is a finite length integral in the upper half plane. And so anything I plug into here, that's, as long as it's a holomorphic modular form, could be weakly holomorphic even, that's going to converge because these are finite integrals. So I'm going to plug in Jm of tau, and then d tau over q tau 1. This differential is invariant under, if we pick different representatives for our classes, then this differential won't change. Okay, so these are the traces, these are the objects that we care about. But I haven't told you what we're going to do in the square case. So let's say that really quick. So if little d times big D is actually a square, well then this integral that you want to plug in, well, it's not going to converge because you're taking an integral whose endpoints are at cusps, and you have something that is not a cusp form. It doesn't vanish at the cusps. In fact, it's the opposite. It blows up at the cusps exponentially. So this integral does not converge in a spectacular way. And so what we're going to do is regularize it. So and one way to do this, there's a couple of ways to do this, but one way to do it is to let Jm q of tau be the function Jm of tau minus a sum over the alphas that are the roots of q. Okay, so these are rational numbers, or maybe infinity if we allow 1 over 0. And if I have such an alpha, I'm going to let gamma alpha be the matrix. Well, I don't actually care what's in the upper row of the matrix, but S minus R will be in the lower row if alpha can be written like R over S, where we allow S to be 0. Okay, and then in this sum, what I'm going to do is subtract hyperbolic sine of 2 pi m times imaginary part of gamma alpha tau, and then E of m times real part of gamma alpha tau. It's not obvious from looking at this that this is the right thing to look at, but it turns out that these are the two things that we're subtracting off are exactly measuring the exponential growth of the j function at the two cusps of CQ, or the two endpoints of CQ. And so it turns out that this function, well, now that we're allowed to plug that in to the integral, and we'll get a finite integral. The problem is that we've just subtracted off something that's not modular, and so it turns out that this new thing is actually not a modular function. But after you sum over all of the Q's, all of the classes, it turns out that this is actually still invariant. So even though we're summing something that's not a modular function, we still get a nice invariant. And so I think what I'll do for the notation here is I'll just put a little Q here, and we'll just understand that in the case where we need a Q, we'll put it, and in the case where we don't, we don't need to worry about it, and then I can just take this condition off here. So now this gives us a description of the traces in both cases. Okay, any questions about that? All right, so here's a theorem, which I think is really a beautiful theorem of Duke, Imamoglu, and Toth. This appeared in the Annals. And then you need something else. Maybe I'll put plus epsilon in order to deal with the squares, because they don't actually deal with the squares. So here's the theorem. If D is positive, if D is fundamental, then the function, let me define a function for you, fd of tau. So this will be the sum over little d's that are positive. And when I write this, I'm implicitly always, little d is always 0 or 1 mod 4 from the beginning, and big D is always going to be a fundamental discriminant. So I'm not going to put the conditions there, but this is really over little d's that are 0 or 1 mod 4. I put in the traces here of J1 q to the little d. This is a Mach modular form. Of weight 1/2 for gamma 0, 4 in the plus space. You can actually just see from the definition that it's going to be in the plus space because all the d's are 0, 1 mod 4. And I can tell you what its shadow is. With shadow, we'll call it g sub d of tau. And this will be q to the minus d plus sum over the negative little d's, tr little d big D J1, q to the minus d. And this is a weakly holomorphic modular form of weight 3/2, also in the plus space for gamma 0, 4. Okay? So somehow the shadow, the shadow is picking up the imaginary traces, or the quadratic imaginary, or imaginary quadratic information. So that's these, the traces of singular moduli, and these are the subject of that paper that Michael mentioned in his talk, traces of singular moduli. So these functions appear there. And then this Mach modular form has all of the real quadratic information in it, so these here. Okay, I just think this is a really beautiful theorem. Now you might be wondering, what does epsilon mean? Well, there's a couple of ways to deal with this. So epsilon is, well, you can either use a paper of Bruinier, Funke, and Imamoglu, where they regularize the integrals for the square cases, or you can use a little paper that I wrote that does something similar, and this is the construction that's in that paper that I wrote. And all that my paper does is the square cases of this theorem, and this paper of Bruinier, Funke, and Imamoglu is very general and handles a lot of other things. So that's a great paper if you'd like to read it. Okay, so my goal for the rest of the talk is to give you the proof of this, or at least most of the details of the proof of this theorem. I think not only is the theorem beautiful, but I actually think the proof is really quite nice too. So are there any questions about the statement of the theorem or anything else we've done so far before I move on? That's a good question. So when D is negative, big D is negative, then you might have the case where both discriminants are negative. And there hasn't been a trace defined for that, at least on this board. But there is a follow-up paper of Duke, Imamoglu, and Toth in which they define. So in that case, you would still have a positive total discriminant, but the two factors are both negative. And there's a geometric invariant that goes along with that that's actually an integral, a surface integral of these J values. And that's a beautiful paper as well. It's called Geometric Invariance and then something and something, something. It's been done, yeah. So the first thing we want to do, oh, you know, I didn't tell you, okay, so I didn't tell you one more thing, I forgot. So this is just one, this is just m equals 1. What happens if we look at other m's? Well, it's a little bit more complicated, but the traces of the JMs, well, they give you coefficients of, let's see, how do I want to actually put this? Because it's a little bit complicated. I don't think I want to actually write the whole thing. Yeah, so these give coefficients of Mach modular forms that are of the form f, say n squared d where n divides m. And these traces are not exactly the coefficients, they're sums. They're like divisor sums of these things. So it's a bit more complicated, but you can look in the paper for the exact statement. Okay, so the first thing we want to do is write Jm as a linear combination of Poincare series. And maybe after, I think this is the fourth talk that I've given this week in which we've used Poincare series. So maybe a theme is you should study Poincare series and know how to use them as a tool because they're very useful. Okay, so what are these? So we're going to let GM tau s. Let's let this be the Poincare series for a certain seed function, which I'll call phi ms. Let's say the weight is 0. Let's see, the multiplier system is trivial, and the group is SL2Z. Okay, where phi ms of tau is, well, it's going to be a different phi ms of v, e of minus mu, and phi ms of v is either v to the s if m is 0, or it's much more complicated, 2 pi absolute value of m to the s to the 1/2, v to the 1/2, I Bessel function s minus 1/2 of 2 pi absolute value of my if m is not equal to 0. We've seen examples of these where we use an extra parameter s. I don't know that I've written down this exact thing before, but it certainly lives in the family of Poincare series that we've studied this week. It's the same kind of flavor. And then what we're going to do is let Jm tau. Oh, I said y, didn't I? Oh, I said I was going to do that a bunch of times, and there it is. Okay, yeah, y is v. Okay, let Jm tau s be, well, we're going to take this Gm tau s and subtract off 2 pi to the s plus 1/2. This is a mess, but I'm just going to write it down. M to the 1 minus s sigma 2s minus 1 of m over gamma of s plus 1/2 zeta of 2s minus 1 multiplied by G0 tau s. Okay, why do we care about this thing? Oh, and what are all these pieces? So sigma is the divisor function where the exponent is 2s minus 1. So these are the sum. This is the sum of divisors of m raised to the 2s minus 1. We have a gamma function, a Riemann zeta function. And so we're really just taking a linear combination of these two Poincare series. Now, what we're eventually going to do, and by eventually I mean like the next line, but eventually we want to take s equals 1. Because at s equals 1, this seed becomes holomorphic, and this Poincare series will give us a weakly holomorphic modular form. So it's a little bit silly to see a zeta of 2s minus 1 down here, because when you plug in s equals 1, this is zeta of 1, which is a pole in the denominator, so it's a 0. This is just going to kill this whole thing. Well, it turns out that the G0 function also has a pole at s equals 1. So this 0 actually cancels that pole, and so this sort of thing makes sense. What this ends up doing if m is not 0 is it just ends up actually canceling out the constant term of Gm. It kills the constant term. So this you can sort of ignore this, and we're not going to deal with it too much today, but you should just be aware that for technical reasons, that's what we need. So you can show using various methods. One way is to work out the Fourier expansion like we did on Tuesday. You can show that Jm tau s has an analytic continuation, and that we're allowed to plug in s equals 1. And so we'll do that. Jm tau 1, it turns out, and it's not too hard to show, that this is just exactly Jm of tau, which is the thing we want. And so we've written Jm as a linear combination of Poincare series. For the calculations that we, I don't think I ever said real S should be bigger than 1 in the Poincare series. For the calculations that we do, we're going to leave the S in so that we have things like absolute convergence, and we can exchange orders of sums and integrals without worrying. And then at the end of the entire argument, we'll plug in S equals 1. But really, this is to show us that once we plug in S equals 1, we're going to get what we want. Right. Oh, I can say one more thing. This is kind of a weird thing to do over on this side when we're just looking at Jm. It's not at all clear that this is the right thing to do, but it turns out that these two alphas that are the roots of Q, they correspond to two of the matrices in the sum for the Poincare series. Exactly. And so what this construction does is it actually just fixes the Poincare series by just deleting those two terms entirely. It just takes them out. And so I'm not going to write it in the notation here, but that's essentially what we're doing, is we're constructing this using a Poincare series that we've modified by removing two of the terms. And I'll try to indicate in the calculation where that ends up mattering. Okay, so what we want to do is actually we're going to compute these numbers directly using the definition of the Poincare series. And the one that's slightly more interesting is the second one. It's a little bit more complicated. So that's the one I'm going to do. And I'll try to indicate how this calculation goes as well. It's actually quite similar. But we're going to do the cycle integrals calculation. So let's compute the integral over CQ of the Poincare series phi ms of tau. And I'll write d tau q, and this just means d tau over q tau 1. This is this invariant differential that we can play around with. Okay? Let's unfold the Poincare series, or the definition of the Poincare series. So this should be the sum over gammas mod, gammas in gamma mod gamma infinity. And then we will integrate over CQ phi ms of, let's see, phi ms. I'm taking this bit here, so I want to do imaginary part of gamma tau, and then E of minus m real part of gamma tau, d tau q. Okay. So the next step is to take this CQ, which remember is just a portion of the arc, and we're going to take a bunch of little choices of the portion. So what we did is we took SQ and we broke it into infinitely many pieces based on this infinite cyclic group. We're going to take all those pieces and add them up so that we get the entire arc SQ, because it's much easier to describe SQ than it is to describe CQ. And the way to do that is to just mod out on the right by gamma q. And then that's going to sum all of the different CQ representatives that we have until we get SQ. Yeah. And then, I'm just going to write this for the integrand didn't change, and so I'm not going to write it over and over again. Okay, so then now if we want to take the entire trace, so I want the sum over q's in QDD mod gamma, chi dq integral over CQ of P phi ms tau d tau q. Okay, well, this is going to be the sum over q's let's see, what do I, I don't actually, okay, yeah, you need to Yeah, all right, let's think about this for a second. So if I now take, yes. Okay, I actually do want to write down what that is. Sorry about that. Let's write it. Phi ms, imaginary part of gamma tau, e of minus m, real part gamma tau, d tau q. So now what I'm going to do is actually do a change of variable in which I replace gamma tau by tau. So everywhere I see gamma tau, I'm going to replace it by tau. Okay? But there's taus here, and there's a tau here, and this invariant differential, it turns out that what you end up getting is gamma q if you do the replacement in that way, and this q also becomes gamma q. So that's not too hard to check just using the definitions of things. So when we do that change of variable, it changes every instance of q into gamma q. Okay? So now I'm going to sum over all the q's in this finite set. Okay, well, I'm also summing over all the gammas in this set. So we're almost getting every single quadratic form, except we're not getting the ones that are equivalent mod gamma infinity. So we're almost summing over every quadratic form in this set, except we still need to mod out by gamma infinity because we're not summing over the gammas in gamma infinity. Okay, that's something that. Where did this come from? Oh, so yeah, this part of the calculation is just maybe the inside. Is just if I look at this part. And now that I've computed this part, I want to start computing this part. Yeah. So I'm adding that in. Yeah. So this is not a continuation of this line. Yeah. Right. So now I'm summing over a lot more q's. I'm only modding out by gamma infinity, which is a much smaller group. Okay. And then we have integral over now SQ, because I'm summing over a bunch of gammas. And then now the integrand does not change. All right. So we've gained a couple of things here. One thing that we've gained is that SQ is easy to describe. We have an explicit formula for it. And now actually this set is also much easier to describe than Q mod gamma. There's an explicit description of this as well. So we're going to do those two things in the next two steps. So let's parameterize A, absolute value of tau squared plus B, real part of tau, plus C equals 0 in the following way. So let's let tau q be minus b over 2a plus I square root of little d big D over 2 absolute value of a. This is a point now in the upper half plane. It's no longer a root of q, because remember q is indefinite and it has real roots. This is an imaginary number. But it turns out that this point, this is the apex of the circle, of the semicircle, SQ. So it's the very top point of the circle. And so we're just going to parameterize relative to tau q. So the parameterization is going to look like tau equals real part of tau q plus, well, plus or minus e to the plus or minus I theta, imaginary part of tau q. And you can check that this actually does parameterize that circle. And then we choose plus or minus based on the sign of A. Okay, so this is going to parameterize the circle, and it's going to do it in the correct orientation, as I said before. And then you can check that d tau q turns out to be 1 over square root of little d times big D, d theta over sine theta. So we've also gained a really nice looking differential as well. Okay. I'm skipping calculations that are reasonably elementary. You can just kind of check these. This is algebra. Now let's look at this set Q, D, D, mod gamma infinity. It turns out that there is a one-to-one correspondence to the set of pairs A and then B mod 2A. Let's say A greater than or equal to 1. I did not write that like a set, but I think you get the idea. Yeah, maybe I can just put set things around it. So the idea is that you pick an A that's 1 or bigger, and then you take all of the B's that run mod 2A. And the correspondence goes that a Q over here, a pair A comma B over here corresponds to A, B, and then whatever C has to be in order for the discriminant to be little d times big D. So we don't actually care about this third thing. Okay. Now this is the point at which the square discriminants things comes up. Remember I said that we deleted 2 terms from the Poincare series, and it turns out that those two terms correspond to A equals 0. They correspond to A equals 0. And so you're essentially removing A equals 0 from here. The A equals 0 term doesn't happen in the non-square case, but in the square case, this correspondence includes A equals 0. And so this deletion just removes that. And now actually it's a uniform proof for the rest of the thing, because now we're looking at the same set for the rest of the proof, which is kind of fun. Okay, I'm going to leave this statement of the theorem up, so I'll leave this statement of the definitions up. Okay, so what do we do with this? So if I take, I was computing here, so let's call this star, and I'm going to keep going. Star equals, okay, so it's going to be a sum over all A's from 1 to infinity. And then, maybe I'll do that step second. So let's do a sum over Q's in Q little d big D mod gamma, chi dq, E of m, real part of tau q, times the thing that I'm going to call capital phi ms of imaginary part of tau q, where phi ms of let's just say t is the integral from 0 to pi of phi ms t sine theta times cosine of 2 pi mt cosine theta, iterated cosines, d theta over sine theta. Okay, where does this all come from? Well, this comes from the parametrization step. So we're parametrizing the arc of a semicircle, so that's why we're integrating from 0 to pi. Here's our differential. You can, let's see, when we want to work out the real and imaginary parts of this, you break the e to the I theta into cosines and sines, and that's where the cosines and sines are coming from. I guess one thing, I think I forgot to put 1 over square root of little d times big D, because that comes from d tau q. And then maybe one other step we're going to do is say this is 2 times the sum over just the quadratic forms who have A being positive, because there's a symmetry between Q and minus Q that's respected by chi, and you can check that, that things work out nicely, and you can just sum over 2 copies. And so that actually means that over here, I've written something wrong. This is really a bijection between QDD plus. So you're wanting to take all of the positive A's. Otherwise, you would take a bunch of negative A's as well. Gamma infinity. Yes, thank you. Thanks. Okay, Now let's talk for a minute about what you might do in the imaginary quadratic case. Well, here we're just plugging in tau q. We don't need to do any parameterizations or anything. We're just plugging tau q directly in. And it turns out that you're going to get something that looks exactly like this, except instead of an integral here, this is just going to be the original function little phi evaluated imaginary part of tau q. So it looks strikingly similar to this thing. And so actually at this point, there's a way to sort of take the two proofs and they just kind of converge into one proof at this point, where this is an integral in one case and it's just evaluation in the other case. Again, I'm not going to go through the details there, but I just want to give you a hint of how that works. Oh, minus. Yeah. Yeah, there's so many little details here, a lot of things to mess up. Okay, so now I think we're ready. I think we're ready to use this parameterization. So we'll take all the a's that are greater than or equal to 1. Let's see, the imaginary part of tau q does not depend on a. Yes, it does. What am I talking about? No, it doesn't depend on b, is what I meant to say. Yeah, the imaginary part of tau q does not depend on b. So before I do the sum over b, I'll take this phi ms term out. Imaginary part of tau q. And then we can sum on the b's mod 2a. Okay, and then we have chi d of, and now instead of writing q, I can actually write down exactly what the quadratic form is. It's a, b, and then c has to be b squared minus little d times big D over 4a. So in order for this number to be an integer, the only b's I'm allowed to take are the b's for which b squared is congruent to little d times big D mod 4a. Is this sum starting to look familiar? We've seen something that looks like this a couple of times, these sums that are over quadratic congruences. We've seen a couple of these before, so that's no mistake. And then I still have an e here, so this is going to turn into e of minus mb over 2a when we compute the real part of tau q. Okay, I'm going to borrow this 2 and actually put it here. And then maybe if you don't mind me continuing to erase and change things, I'm going to borrow this 2 again and change this b mod 2a to b mod 4a. I'll just sum over the same thing twice. And that'll give me 2 of the original thing. So I'll just take that 2 and just sort of put it in the summation here. This is exactly the sum that I called Tm little d big D. Well, I called it, yeah, this would be 4a. Maybe I need to remind you. Let's see. I will write this with a C here, and I'll say this is Tm little d big D 4a, and then the definition I'll remind you of is that this is the sum b's mod c such that b squared is congruent to little d times big D mod c. Chi d of c over 4 b squared minus little d big D over c, and then e of minus 2mb over c. And I believe I had this exact sum, or maybe in a special case, written up for you. I can't remember what day that would have been, maybe second day or the third day. Okay, so what we end up getting here is now 1 over square root of little d times big D, sum over all positive c's that are divisible by 4 of Tm little d big D c times phi ms of 2 square root of little d big D over c. Okay, so we have now two pieces here that we're going to deal with completely separately, because this piece here is an integral. Let's see, it's an iterated integral, or it's an integral of iterated cosines. Anytime you see something like that, there are Bessel functions lying around. And so this is going to evaluate to, with a bit of work, this evaluates to the J Bessel function. And then actually in the case of negative discriminant, remember I said there's no integral and we're just plugging the tau q's into the seed. And remember the seed was already an I Bessel. So in that case you get, well, you already had an I Bessel, and so you still have an I Bessel. Okay? And then what do we do here? Well, I think I told you before that there's this thing called Conan's identity. And I'll tell you the general version of it now. I think I had it in a special case before. But Conan's identity looks like Tm little d big D C is equal to a sum over all n's dividing the GCD of m and c over 4, d on n, there's your Kronecker symbol, and then square root of n over c, and then s plus of d m squared over n squared big D c over n, where s plus means the plus space Kloosterman sums. So these are the half integral weight Kloosterman sums for gamma 0, 4 projected into the plus space. It's not too surprising that we'll see something like this with m squared over n squared, because remember that big D is a fundamental discriminant. It doesn't have any square factors in it except maybe a 4. Well, now as m runs over all possible values, this is going to give us actually every possible input into the second thing. So that's nice. Okay, well, what have we come up with? Well, now we have a sum over C's of some Kloosterman sums weighted by Bessel functions. We've seen that before as well. These are the Fourier coefficients of Poincare series, but now these are Fourier coefficients of half integral weight Poincare series in the plus space. So this is where I'm going to stop writing formulas, and I'm just going to put, this is a coefficient of half integral weight, or I can even tell you what weight it is. It's weight 1/2. Coefficient of a weight 1/2 Poincare series in the plus space. And it's not quite so easy because, again, there are these convergence issues because we're in weight 1/2, and I told you that that's one of the bad weights. And so you have to do things with convergence and analytic continuation. And so there's still maybe a couple of pages of work, but ultimately this is the big picture, is that when you compute these cycle integrals, you just get the coefficients of these Poincare series just visibly showing up. And that's how you can prove that theorem of Duke, Imamoglu, and Toth. Let's see, what else did I want to say about this? I do have a few more words to say about this, because I do have a few more minutes. Are there any questions about this before I move on? So maybe I'll just take a few minutes to say a few words about some work that I've done on these traces of cycle integrals. And that's on the asymptotic distribution. Okay, so in this paper of Duke, Imamoglu, and Toth, they conjectured that the traces, and I'll just put one, I'll just put a little d here. So these aren't the twisted traces. These are just the usual, they're the untwisted ones. So we'll say like big D is 1 in this case. They conjectured that this is asymptotic to minus 24 sigma 1 of m times 2 log epsilon d times h of d. So here, this is the class number of q adjoint square root of d, and then this is the regulator also of Q adjoint square root of D. This is the divisor function again. And this 24 actually does have some significance. It shows up in a similar problem in which we think about the asymptotic distribution of the traces of singular moduli. So if you look at these as they get bigger, there's a 24 that pops out in the formula. This was a theorem of Duke. And so they were thinking about, well, what about the asymptotic traces of cycle integrals? And this 24 seems to also pop out in the same thing. So this should be as d goes to plus infinity, or as m goes to plus infinity. And here we should have d positive if we do that. So you should be able to take either one of these variables to infinity, and you should get the same asymptotic behavior. Now, this is also quite interesting. These numbers are pretty small, whereas the corresponding numbers for the negative discriminants are quite large. These are exponentially large, and these are quite small. So it's like these are behaving like cusp form coefficients, and these are behaving like weakly holomorphic modular form coefficients. And that's not too surprising because the space that this Mach modular form, or the associated harmonic Maass form lives in, it's really the H sharp space. And if you recall, these are the ones for whom the shadow is a weakly holomorphic modular form. The growth happens in the non-holomorphic part, and there's no growth happening in the holomorphic part. And so actually it's not too surprising from that standpoint that these numbers should be pretty small. And in fact, this theorem, or this conjecture, would say that. Well, how do you prove something like this, or how do you attempt to prove something like this? Well, you can write these traces in terms of sums of Kloosterman sums, and you can try to get cancellation in the same way that we were talking yesterday. You can try to measure the cancellation in the signs of the sums of Kloosterman sums. So this was worked out. So in the d going to infinity case only, this was worked out by Duke, Friedlander, and Vonich. And this is not the only theorem in that paper. It's one application of their main theorem. And they got a power-saving error term of d to the minus 1 over 5,325. So a pretty small exponent there. But they were able to get a power saving. So meaning that there's an error term of size this multiplied by the size of this. Okay. And then this was done independently around the same time and using different methods by Riyad Masri. And his power saving error term was d to the minus 1 over 400. So quite a bit better. So Bill Duke and I were interested in this problem, and so we decided to take a crack at it. And so we wrote a paper that appeared in 2020. And we proved the following generalization. So we can do this for the twisted traces, so including the big D. So this equals minus 24 times delta D equals 1. So this main term is only going to show up if little d is equal to 1. Sigma 1 of m. Let's see, I think I've now switched my d's, because now I think I want big D to be the thing that's going to, well, I'll fix that in a second. 2 log of epsilon big D, h of big D, plus big O of m to the 8/9 big D to the 13 over 27 times little m big D to the epsilon. And this is as little d times big D goes to infinity, or, well, okay, this is just true. It's just true, okay? So it's just true all the time. So the point is, if you want to take big D going to infinity, then you'll get a power saving error term here. So what is 13/27? Well, it's 1/2 minus 1 over 54. So the power saving is d to the minus 1 over 54. Why 1/2? Well, because that's the approximate size of the class number, or the class number times the regulator. Notice also that 8/9 is a power saving on the approximate size of the divisor function, which should be about size m. And so this is also a power saving in m. And so this makes sense as an asymptotic formula if m is going to infinity or if d is going to infinity. And that answers this conjecture of Duke, Imamoglu, and Toth in both aspects, and slightly beats both of these error terms. Well, how did we do it? Well, we very carefully studied the sums of these Kloosterman sums using the spectral theory of the Laplacian, and lots of work. And I don't have time to tell you about it, so I won't. That seems like a good place to stop. So there you go.
Thanks a lot, Nick. So there's time for a couple of questions. The Duke Imamoglu Toth paper, they construct a mock modular form of half.
Yeah.
Using this procedure.
Yes.
Have like some higher weight mock modular forms been constructed using like say 3/2 weight using this approach?
Yes. So this sort of thing also holds in other weights, and there are various papers about that. I think maybe you want to talk to Balesh actually about that, right? In other weights. Yeah.
So if there are no other questions, let's thank Nick again.